Thank you, everyone. Thank you for coming to my talk. I'm Suma Chen from the Xi'an Institute of Optics and Precision Mechanics, which is an institute of Chinese Academy of Sciences. And we also belong to a key laboratory of space precision measurement. So today we are going to talk about the single photon imaging, especially on the applications and its challenges. First of all, I would like to have a brief introduction of the background of this technique. As we all know, for the optical imaging, we will have passive imaging and active imaging. So for the passive imaging, it's strongly affected by the environment. For example, if it is in night, we will see nothing. For the active imaging, we will see that the transmission power falls rapidly with the distance. So in a word has a limitation on the sensitivity. So in the applications like long-range imaging, it will have a severe power attenuation. And for example, for the underwater surveillance, for the deep sea, may have no incident light. So the passive optical imaging is not practical. Or with the limited power, so the active imaging cannot be used as well. And for other things like emitter use, so to solve the problem, we have two solutions. The first solution is using the high power laser, but it's not always practical. For example, for its weight or its for the materials, for lots of reasons. So the second solution will be the improving the sensitivity of the detector. So we have a single photon detector. Well, here we need to be clear that single photon imaging is an advanced field of LiDAR. That means light detection and ranging. So it's also named as a single photon LiDAR. So we call it SPL in short. And once we see that the optical system is much like a conventional LiDAR, but the difference is that we are using a single photon detector. So we have high sensitivity. And for another, we need to see that we have discrete pixels in a spatial domain, and we also has discrete in the range dimension. So we mention have a one-time beam, which means that this is a histogram, is a discrete one. So once you are accumulating enough photons, then you have the amplitude of the peak. Instead of measuring the peak directly, the histogram is formed by accumulating enough photons. And the characteristic of this technology we can summarize as follows. First of all, we will have a single photon sensitivity is clear, and has a picosecond timing resolution. As we all know that the time delay refers to the distance. We'll have depth which is lower than 1 millimeter, and the optical power, it means the average power, is just microwatts to milliwatts. So it's avoid damaging the target. And we need to emphasize on that the detector has a boundary response. The spot, which is called single photon avalanche diode, do not record the amplitude, but only responds to whether it receives a photon. It means that only 0 or 1 states are recorded. And that leads to the final characteristic, which is that the imaging quality can be improved by accumulating enough photons. We have a principle called time-correlated single photon counting technique, which is shown as in the right figure. Here is an ideal signal. But these are different detection cycles. For each cycle, we only receive some sparse signals. Once we accumulate enough signals, we can recover the histogram, which has plenty of information from the ideal signal. And that's the principle of TSSPC. In other words, it's probabilistic imaging, because every cycle is a random signal. So once you sum them up, it will be no longer random, but in each cycle is random. And here are about the significance. In short, we have three significance about this technique. is high sensitivity, high resolution, and high efficiency. First of all, we have a quantitative sensitivity, so it enables the applications like long-range imaging or imaging through scattered media. Second one, we will have a compacted design because we have quite low power consumption, as we just mentioned. The optical power is just microwatts to milliwatts. And we can use some smaller lenses because we can improve the SNR by accumulating the photons. And the detector is usually fabricated using CMOS technology. And we also have some new designing principles. First of all, in conventional LiDAR, we usually discriminating the signals by using high SNR. It means signal-to-noise ratio. So we just simplify discriminate the peaks. But here we are trying to fully utilize all the resources instead of increasing the hardware alone. And it's impossible to imaging with 14 per pixel lower than 1. It means that beyond the imaging theory. And it also arising new technologies like non-line sight imaging and single pixel imaging. So here is about some the progresses of the applications. For long-range imaging, it started from the MIT Lincoln Laboratory, which is 2022, which is an outdoor experiment, which is only 60 meters. And here at Walton University did lots of work, which is over 4 kilometers, 10 kilometers. And the USTC, which is University of Science and Technology of China, has performed single photon imaging over 200 kilometers, which is published on Optica this year. And the optical power is just around 600 milliwatts. Another one is imaging through the scattered media. Again, the milestones are made by the Hewlett-Packard University. So they did some experiments in the highly turbid media, like underwater, which the water is from the off the shore seawater, which is highly turbid. So we have a strong attenuation, and we also have a even stronger attenuation, and coupled with some algorithms, we can recover the details of it. And we also perform some real-time underwater imaging, which the speed is around a kilohertz. And except the water, we also have some imaging through upskirts, which has different kind of frogs in the air, and we still can detect some scenes that our eyes cannot see. So here are some examples. And we also perform some imaging with complex scenes like object classifications. It means that we not only have the 3D profile, but also some spectral information for the classification, which has 33 bands. So we have 30 classes, and some multispectral SPL system, which is only using one supercontinuum laser and one detector. And we also perform some camouflage targets, as we can see that a man is standing behind the netting, but we can still able to detect them because we have a quantitative sensitivity. And again, with the USTC, which is performed with long-range imaging with multiple returns, because the speckle might be too large for after the transmission of 20 kilometers. So it contains lots of surfaces. So we have a CNN-based algorithm to solve this problem. And again, we will mention that the non-line of sight imaging was why we call it non-line of sight imaging. We all know that if we see directly on the bunny, we cannot see the bunny. So that we have a non-line of sight imaging, which is reflected from the visible wall and to the target, and then to the target to the visible wall and received by the system. So that is called the non-line of sight imaging, which means that somewhere you cannot see, but we can see it via our system. So it's achieved the first time non-line of sight imaging by University of Wisconsin, which is in 2012. with a strike camera and filter back projection algorithm. And the other milestones are made by Stanford University, which is called FK migration algorithm and RCT algorithms. We will introduce them later. So here is the real-world object, and here is the reconstruction. Aside from that, we will have some high-speed imaging. For example, here, again, here at Walton University, they're standing 300 meters away, and with some milliwatts power, we will have a 50 hertz video rate. We will able to see some people behind the net, and yes, the video cannot be played. We will have some high-speed, high-resolution video, which is around 1,000 frames per second, which is achieved right here at Walt, and some real-time reconstruction with limited resources because they are implemented on the FPGA-based system, as well as some high-flux imaging from Boston University, which increased the flux, which is 2 orders higher than conventional wisdom. So we can improve the imaging speed by improving the efficiency. Now here are about the problems. For example, for the ideal cases, everything is nice. But when you have a strong intonation, like a kilometer imaging or insufficient accumulation, we will have a sparse photon and some strong noise because we are working on single photon imaging level. So we have a backscattering and ambient light like the sun, and multiple returns because we are illuminated multiple surfaces or have a semi-transparent media. Again, with some multiple dimensions like spectral or polarization information, we will have 40 information, which means that 30 information plus some spectral or polarization information. So we here have the table summarizing all the problems. We can see that some of the problems cannot be solved by the hardware alone. For example, for the long-range imaging, for example, you are performing imaging through 100 kilometers away. Of course, it should be sparse, and the noise can be strong, and because you have a big speckle, so you have multiple returns. We have different kinds of the combination of the problems. So the first one is that we can solve the sparse photon, the strong noise, via the special correlations. For example, here is that, as we can see, each pixel are correlated with its neighbors. That is called local spatial correlations. And if they are correlated through all over the image, it will be called as non-local spatial correlations. As we know that each one is correlated, so this can be as a prior in the statistics. So we use a Bayesian inference to restore the degraded images. And the right side is an example that's the restoration results of Open3DR algorithm, which is state-of-the-art algorithm for the non-local spatial correlation restoration algorithms. And we also have some UA or CNN-based algorithms from different authorities. We know that. And yeah, we have some multiple returns. So we have 3 kinds of solutions. The first one is much like with the sparse photon and strong noise. We can restore them with the sparseness assumptions and the spatial correlations. For the state-of-the-art method will be the NR3D. For example, here we will have some sparseness assumptions, and then we restore them using spatial correlations. And then we can see the map behind the netting. And the second solution will use the point cloud processing from the computer graphic communities. And the representative algorithm will be Manipop. And third one will be the use of deep learning methods. For example, the LaterNet for some complex scenes, the CNN-based algorithm and LaterNet could obviously we can distinguish those peaks. And for the multiple dimensions, the first one would be that we can enhance the performance of 3D imaging. For example, here, the convolved considered the polarization imaging. The polarization information are included during the imaging, which is by the Wuhan University in China, and just do the denoising things because we have some polarization information. And we can also reconstructing the 4D images, like full color 3D images, using like MusaPop or multi-scale or fusion-based method. These are the results of the reconstruction. And we can also have some applications with extra dimensions, like some material discrimination, because we do not only have the 3D profile, but also have some spectral information, which is an advantage because we have 4D information. But non-of-sight imaging is new imaging application and usually achieved by the single photon imaging. So the first idea will be that reconstruct with back projection and filtering, which is called FBP in short, and invented by the University of Wisconsin. The second one will be building a forward model, and then we can solve it by using inverse problems method, like LCT and FK from the Stanford University. And third one will be the virtual wave, which is a new idea that assuming that during the transformation, there is a virtual wave exists. So we have some phase information, so we can have a better reconstruction. And this also from the University of Wisconsin. And we can also reconstruct them with some geometry informations. The representative method will be the Fermat path-based reconstruction, which is from the Carnegie Mellon University. And we need to mention that it's the best paper in CVPR 2019. So for the prospects for the future one, we will have some high performance detectors because we can have some bigger size of array with lower atomic jitter and lower noise. That's what we expected, and is keep on moving. And we will have some better system design, like scaleless, thanks to the bigger size of array and the compact integration for the system and the detectors, because the detectors are fabricated using CMOS. And we can design some powerful algorithms. For example, the combination of the above problems, like the combination of the sparse photon and the store noise. And the algorithm have to balance on the speed and quality, and have to face on like some resource constraints. For example, if you are working with the FPGA-based system instead of the computer, which is high performance. And we have a crossover with other disciplines, like computational imaging to overcome some resolution limitations, because right now the size of the array is not big enough. So we can perform some super resolution, and we can combine with AI to have some smart imaging method. For the future development, we will have a lower cost. We are trying, and we can fusion with other modalities to achieve some other kinds of applications. And for the applications, we will have plenty of it. For example, the autonomous vehicles, terrain mapping, and atmospheric monitoring. So we have plenty of it, and they have a bright future. So that's all for today. That's all by my presentation, and I'd like to thank for the other co-authors from our laboratory. And if you have any problems, just don't hesitate to contact me via this email. Thank you everyone. Thank you for your attention.